starting with y prime equals x squared minus 4, 3y plus 2. Okay, so first we're going to separate our variables by moving our terms opposite sides of each other. So we're going to start with dy over dx equals x squared minus 4, and then 3y plus 2. And then next we're going to do dy over 3y plus 2 equals x squared minus 4 dx. Okay, perfect. Then this gives us the integral of 1 over 3y plus 2 dx, sorry, dy, and integral of x squared minus 4 dx. Okay, perfect. Now we're gonna integrate both sides, both left and right. So let's label this left, and let's label this right. Okay, so for the left side, we're gonna use u substitution. So let u equals 3y plus 2. Oops, there we go, plus 2. du equals 3 dy. dy equals 1 over 3 du. Okay, so starting with our integration, we have integral of 1 over 3y plus 2 dy equals 1 over u, 1 over 3 du equals 1 over 3 ln absolute value equals 1 over 3 ln 3y plus 2. Okay, and now for our right side, we have the integral of, x squared minus 4 gives us dx equals integral of x squared dx minus integral of 4 dx, which then gives us x cubed over 3 minus 4x. Okay, perfect. And now that we have our two integrated values, we're going to combine them. So 1 over 3 natural log constant value 3y plus 2 equals x cubed over 3 minus 4x plus c. And now we multiply both sides by 3. So let's write multiply every term by 3. Okay, so let's start with 3 times 1 over 3 natural log constant value 3y plus 2 equals 3 x cubed over 3 minus 4x plus c, which gives us ln 3y plus 2 equals x cubed minus 12x plus c. 12x plus c. So after multiplying both sides, the left became this and the right became this. And, oh, yeah, we didn't forget our constant of c. So now we're in the part where we apply e to both sides. So we go ahead and write e ln constant value is 3y plus 2 equals e to the power of x cubed minus 12x plus c. Okay, then this essentially gives us natural log 3y plus 2 and e to the power of c ex cubed minus 12x. Okay, there we go. Okay, so now we let A equals e to the power of c is greater than 0. And then we drop the absolute by allowing c. This just means that c is an element of a set of real numbers that excludes 0. So then this just gives us 3y plus 2 equals c x cubed minus 12x, which then gives us our final answer of yx equals 1 over 3 cex cubed minus 12x minus 2. Up next, we're going to do y prime plus 4y equals e to the power of negative x, and y of 0 equals 4 over 3. So to start this off, we're going to write it off in standard form. So we're going to write y prime plus p of x, y equals q x with p of x equals 4 q of x equals e to the power of negative x. And right underneath that, we're going to write mu of x equals e to the integral of p of x dx, which equals e to the power of 4x. So now we're going to multiply by the ODE by mu. Sorry, we're going to multiply the ODE by mu. So we're going to do e to the power of 4x y prime plus 4e 4x y. Let's read this better. There we go. Y equals e to the power of 4x e to the power of negative x equals e to the power of 3x. And now we're going to do the left side, which is a product derivative. So let's do d over dx and e to the power of 4xy equals e to the power of 4x prime y plus e to the power of 4x y prime equals, sorry, what? Let me erase this. There we go. Y prime equals 4e 4x y plus e to the power of 4x y. There we go. Okay. So what we did basically is we wrote p equals 4, q equals e to the minus x, and by integrating the factor mu is e to the integral of p, so that's e to the 4, and we multiply through, the left side becomes exactly a derivative of e to the 4 times y. I'm sorry, e to the 4x times y, verified by the product rule. Let me get better view. So let's go ahead and integrate and solve. So let's go ahead and integrate both sides. So we're going to integrate the integral of d over dx e to the power of 4xy dx equals the integral of e to the power of 3x dx, and this is equal to e to the 4xy equals 1 over 3 e to the power of 3x plus c. So let's go ahead and let's divide by e to the power of 4x. So by doing this, we're going to do y equals 1 over 3 e to the power of 3x e to the power of negative 4x plus ce to the power of negative 4x equals 1 over 3 e to the power of negative x plus c e to the power of negative 4x. Okay, now, let me make sure I'm still in frame. Okay. Now we're going to apply y of 0 equals 4 over 3. So for this, we're going to do 4 over 3 equals 1 over 3 e to the power of 0 plus c e to 0 equals 1 over 3 plus c equals 1. So our final answer is y of x equals 1 over 3 e to the power of negative x plus e to the power of negative 4x. And a brief little explanation to show my understanding of the existence and uniqueness of first orders. So existence and uniqueness hold wherever the denominator 1 minus 4xy isn't 0. So any region that doesn't cross that curve has a unique solution. So here we have 3x squared minus 2y squared dx plus 1 minus 4xy and dy equals 0. So we're going to start off by writing. Now first we're going to check the exactness with the explicit partials. And to do that, we're going to start by writing, there we go, m xy equals 3x squared minus 2y squared and xy equals 1 minus 4xy. And below that, we're going to write m of y partial over partial y 3x squared minus 2y squared close parentheses is equal to negative 4y. And right next to it, we're also going to write n of x equals partial over partial x in parentheses 1 minus 4xy close parentheses is equal to negative 4y. So since m of y equals n of x 1, then this is exact. So we computed m sub y and n sub x, and then both equal negative 4 for y, so the form is exact. Okay, now let's construct the potential f step by step. So first we're going to integrate the m with respect to x. So we're going to write f of xy equals integral 3x squared minus 2y squared dx. And then this is integral 3x squared dx minus integral 2y squared dx equals x cubed minus 2xy squared plus h of y. Okay, now let's differentiate with respect to y. So in respect to y, we're going to put f of y partial over partial y x cubed minus 2xy squared plus h of y equals negative 4xy plus h prime of y. Okay, now let's try to match fy to n. And to do this, we're going to do negative 4xy plus h prime of y equals 1 minus 4xy, and then h prime of y equals 1, and then hy equals y plus constant. Okay, plus y, there we go. Okay, and we're going to absorb this into our final constant. So therefore, f x of y equals x cubed minus 2xy squared plus y. And now let's set the solution. Okay, so solution is set f equals c. So that gives us x cubed minus 2xy squared. Oops, yeah, squared plus y equals c. And this is our final answer. So what we did is we integrated m in x to get f equals x cubed minus 2xy squared plus h of y, and then we differentiated in y and set equal to n, and then that forced h prime equal 1. So h is y, and then hence the implicit solution is x cubed minus 2xy squared plus y equals constant. Last differential equation, y prime equals x minus 1 over y, and y of 3 equals 0. We're going to show the theorem's hypothesis fail. So we wrote f of xy equals x minus 1 over y, and at 3, 0, f is undefined. So partial derivative of f over partial derivative of y equals, there you go, negative x minus 1 and y squared. Yes, y squared. Y squared is also undefined. There you go. So according to Lindelof's hypothesis, continuity in y and the local Lipschitz in y fail at 3, 0. So f is x minus 1 over y. At the initial point 3, 0, f is not defined, and its partial y also blows up. The existence uniqueness theorem does not apply here. Solving for y, which is not equal to 0, shown nearby curves, and then showing why IVP has no solution. So we're going to write for y is equal to not 0. We're going to separate. We're going to do y of dy equals x minus 1 dx. And next we're going to integrate. So integrate y dy and integrate x minus 1 dx, and then 1 over 2 the y squared minus 1, sorry, y squared is equal to 1 over 2 x cubed minus x plus c, and now we're going to multiply by 2, so y squared equals x squared minus 2x plus c. Okay, now that we've done this, we're going to impose y of 3 equals 0 algebraically to see the locus. So we're going to do 0 minus 1 plus c equals is equal to 3 y squared, and then x minus 3 x plus 1. Okay, but to check derivative at the IC, we do y prime of x over x minus 1 over y, and then y prime 3 equals 2 of 0, which is, and 2 over 0, which is undefined. So when y is non-zero, separating gives y equals x minus 1 dx. And when we integrated this, we got 1/2 y squared equals 1/2 x squared minus x plus c. And then we multiplied by 2 to clean it. And y squared equals x squared minus 2x plus c prime is what we were given. So then by plugging in the points 3, 0, it forces c prime, which equals -3. So the curve is y squared equals x minus 3, x plus 1. But the derivative formula at x equals 3 divides by 0. So a differentiable solution cannot pass through the initial point. And just overall, therefore, the IBP has no solution, hence no uniqueness.